Hi, I'm Andy Wang, and today I'll be presenting StackingBot. Let's set the scene. So I was thinking about what project to do, and I sort of saw a P set lying there, and it's like, well, wouldn't it be cool if a robot could do a P set for me? I saw the door opening P set, and thought about it, I was like, well, that's not really possible. So if we can't make something that college students can do, what if we made something that babies can do? Well, what do babies do? They crawl around, they cry out quite a bit, they eat Legos. So I went, okay, what if we made a robot that can build Legos, that can assemble Lego structures? Now the challenge was really just how am I going to turn that thing on the left, the stack of Legos, into an actual structure? Let's set the problem. So first, robots don't really have the creativity to build Lego structures. So this creativity is going to be brought in by a human, and it's going to be brought in via the form of a Lego blueprint. So if you look at the bottom left, this blueprint is going to be provided to the stacking bot, and it's also given sort of a list of what pieces to put first, so an assembly order. And the reason for this assembly order is to prevent some really difficult situations where like pieces that are placed don't have bases yet. Second, we're using modified Legos. So the pegs have been reduced from 0.0048 meters to 0.004 meters, and this allows for easier attachment. And finally, we're only considering simple structures where we're only considering things on the top right with the stable attachments. We're not considering the other two cases. Now for implementation, the actual Lego placement needs to be extremely precise. So initially I wanted to try using forward kinematics. This actually failed. And instead I decided to use inverse kinematics for greater precision. Here we use a quadratic cost on the distance from the comfort position. This was inspired by the door opening problem. And similarly, we're going to box the gripper position within a desired position bounding box. And this allows us to ensure that the gripper position is where we want it to be. For a general motion plan, we can't sort of just like tell the arm to go to the Lego and then close it and then bring it to the desired position. We actually need a more divided plan where we move above the Lego, descend, grab the Lego, raise it, then repeat the process to set it down in the desired position. Now for the main challenge. So when I actually tried to use inverse kinematics on sort of like the 8 positions shown here, it caused a lot of wild movements and instability. So for example, it would sort of create these really wild joint movements between different positions. And as a result, it'd sort of get tangled up and it'd be really difficult to progress to other positions, also collide with a lot of other Legos. So I've taken inspiration from the door opening problem once again, decided to divide this up into a lot of intermediate positions that you can sort of see on the top right here, where for maybe like a lower action, it's split into 5 or 10 different intermediate positions that it travels to, which allows for these minimal joint movements in between each position. Finally, with this established, it's really hard to move through the center of the arm. So if you consider moving from the one position to another, sometimes that's going to cross the central axis of the arm. And this actually is very difficult to do and it gets the joints tangled up. So instead, I decided to move to a designated reference point, rotate to another designated reference point, then move from there to the final position. And you can sort of see that arc motion occurring on the top right. And finally, I decided to have a variable bounding box so that when it lowers, you can see it's really precise and close to the pose that it's meant to be in. But when it's moving, it doesn't need to be so precise. So you can see it's not fully following the pose that it's been provided. So just for a quick demo of what ended up happening, this is arranging the pyramid that I showed at the very start, and this has been sped up like maybe 10 times. You can see it's just putting each block, and you can see it's following the arc motion described to prevent the joints from being caught up. It's a little hard to tell because of the low resolution, but it's sort of stacking each block pretty well. And finally, as it places the last block, the pyramid is complete. For some future works, I originally wanted to use reinforcement learning, but I didn't have the time. So this would be an interesting opportunity to explore. Similarly, some Lego structures can only be built with multiple grippers. So I wanted to try that out. And also I could allow for all types of attachments instead of the very simple ones I only allowed in the problem formulation. Finally, maybe I thought about extending it to the real world, which would need sensors to track the Legos, as well as sort of an unmodified Lego representation without the shrunk pegs. And quickly, for some acknowledgements, I'd really like to thank Professor Tedrake for providing the Lego SDFs. Thank you.